to the first presentation. And because we have a smaller group, if you do have questions, please feel free to unmute yourself and ask, or use the chat if you prefer. Can everyone see my screen and hear me okay?
Yes.
Okay, great. So welcome to the third BART webinar. We're going to focus today on subspace constrained reconstruction. And we have a wonderful cast, our usual people. So we're really excited to have you here. And by the way, if you want to make a logo for your slide, you can use the BART Phantom tool to make your logo. All right, so we already started off with some BART installation today. Please let us know if you're stuck. Not necessarily we'll be able to fix the problems today, but if you don't have a working install, a really good place to get help is our mailing list, which I'll show in the next slide. So let us know if that's not working for you. We'd really like to understand what the issues are so that we can address them. I'll give a quick update on some BART related matters, and then we'll go into the interactive demos. Volkert's going to start us off with frequency modulated SSFP subspace reconstruction. Nick will talk about the analytical phantom tool we have and how we can use it to simulate subspace recons. And then finally, Xiaoqing will go over inversion recovery flash. And at the end, we're going to use breakout rooms again to do an interactive exercise based on the inversion recovery flash on in vivo data. And all of the material is available on the BART webinars GitHub. So a couple updates about BART. We just released version 0.7. It has a lot of really useful tools, especially ones that we're using today. So things related to model-based reconstruction and signal simulation, as well as improvements to the backend and continuous integration to try to catch these bugs. And for ISMRM 2021, which is coming up, we'll be presenting during the educational session a software demo on using nonlinear operators, machine learning, and deep learning with BART, and this is a direction we're really excited about. And finally, we encourage you to join the mailing list. It's useful if you have questions about BART, but also questions about MRI reconstruction in more general sense. Okay, so I'll give a quick intro to subspace constrained reconstructions, and then we'll go into the demos. So first of all, I wanted to give an incomplete history. By no means is this all-encompassing, but from what I've been able to see, really the early development on subspace-based reconstruction started with Zipei Liang in the 90s, along with Lauterborough, where they modeled spatial temporal signals as partially separable. So this was kind of the very first start of using these in MR, and Peterson extended that with some of their work. Then we saw the initial applications to parameter mapping in the 2000s, where actually the subspace was used as a way to reduce the dimensionality when there's a known signal model. And then we started seeing more specialized applications, some things that I worked on, but even more recently, MR fingerprinting, where we can really see the benefit of a subspace reconstruction compared to just gridding. And so this has really enabled high accelerations for these advanced applications. And our groups have a couple of review papers if you're interested to learn more about some of the history and some of the earlier citations and how it's being used today. So a brief overview of multi-contrast MRI. We're going to focus on the case where we have a signal model, a physical signal model. So we have our images, which are now a time series that go over a certain signal evolution, depends on the sequence we're using, and then those are encoded into K-space. And so this is a typical multi-contrast imaging experiment where we make measurements at multiple time points, and then we want to reconstruct. And this kind of problem can be really easily addressed with BART using parallel imaging and compressed sensing, where we have our linear forward model and we can add regularization of all kinds, including compressed sensing. But the real drawback of this type of reconstruction is that we're solving for many, many images here. And in that case, our data is highly undersampled because we only have a few measurements in each of these timeframes. And so this is a really challenging reconstruction to do when we're not imposing any structure. Now, model-based MRI reconstruction aims to address this issue, and it does so by actually modeling the physical parameters. They could be tissue parameters and they could be sequence parameters, and they come from some physics model, for instance, the block simulation, the block equations. And in this sense, this is solving directly for the parameter maps. And so it's a significant dimensionality reduction. Instead of solving for all of the time series, we're now only interested in solving for the small number of parameter maps. So that's going to give us a dimensionality reduction, and therefore less scan time is needed. But the problem is that this is a nonlinear model. And so now we cannot use parallel imaging and compressed sensing directly. And so subspace constrained reconstruction, the goal is really to reduce dimensionality in the same way, but maintain this linear relationship. If we maintain a linear relationship, then we can still use our conventional parallel imaging and compressed sensing reconstructions. And so the approach is to represent the signal dynamics, the evolution in a linear subspace. Once that's found, we can reconstruct with PICs, and then we can go back to the time series of images, very much like model-based reconstruction. And the reason this works is because signal evolutions are often highly correlated. So here, a time series of images, if we look at a pixel over time, we can see the signal evolution, and different tissue have very similar, although different, they're still quite correlated signal curves. And so we can represent a time series of images by a small basis or a linear subspace. And this could be a Fourier basis. It could be polynomials like a Taylor series, or it could be data-driven, for instance, through principal component analysis. And when we do this, we can basically model our signal using the block equations where we know the parameters of interest, for instance, the parameter maps like T1 and T2, and we can simulate our curves. And here's one simulation, here's another, and here's a collection of simulations, which really shows the correlation. And now one way to make a basis out of this is to use PCA, where we can take each curve and represent it in a matrix. So each of these time series curves is now a vector in a matrix. And if we take the singular value decomposition of this matrix, what we see is that very quickly the singular values decay to 0. In other words, this is a low rank matrix. And so by taking this principal component analysis, we now see that really our data lives in a low dimensional linear subspace of about dimension 4. And so we can take the singular vectors to form our basis, and this is nothing more than principal component analysis. And so by taking these 4 curves, we can recreate any time series of images from this model. And so our subspace model now is represented by these 4 principal component images and the principal component vectors. If we're able to recover this data, then we can always go through the basis with a back projection to get the time series of images. Now, this is really nice because we've reduced the problem to only 4 unknowns instead of however many time series of images we have, which could be in the hundreds. Now, the way to reconstruct this is the same way as we would reconstruct conventional imaging data. We can use PICs, but now we'll use a basis as well. So it's the same interface as our BART-PICs recon. The only difference is that now we specify the data array containing the basis. And so we do that through this -B argument, and then we can still include the usual compressed sensing regularizations, non-Cartesian trajectories, and everything else that PICs has out of the box. And so by doing this, we can reconstruct these subspace or principal component images. And then we can back project with BART as well, using the FMAC tool, and that will give us the signal evolutions. And so this is a really powerful framework that reduces the dimensionality of our reconstruction by a significant amount and still gets to take advantage of the usual and latest advancements in reconstruction. Now, one word of caution is just to say that not all signal models are low dimensional, so it's not necessarily going to work for any signal model, and that's why it's important to check first that your data really does live in a low dimensional subspace. So this is an example out of one of our review papers on a multi-echo gradient echo simulation. Because of the phase changes, actually, this data is not well represented through a low dimensional singular value decomposition. And that's evident here where we need more than 20 principal components in order to represent this data set. And so now we're not really benefiting from this dimensionality reduction anymore. So that's important to keep in mind. So finally, just to summarize that, we have a subspace constrained reconstruction recipe, where first we evaluate the signal model over a range of our tissue parameters or sequence parameters, and then check to see that it actually does fit a low dimensional subspace model. And if it does, then we can fit it and get a basis array, a basis matrix. Given the basis, we can then reconstruct with BART picks and using the basis. And then finally, we can back project to get to the time series. And optionally, this could then be used to fit to the physical signal model if that's what's of interest in the end. Okay, so I didn't want to spend too much time on the presentation. I think the devil's in the details with these kind of things. So let's go ahead and get into the interactive examples. So just to summarize them again, we'll start with frequency modulated SSFP with Volkert. And then we'll go into analytical multi-contrast phantom simulations with Nick. And finally, inversion recovery flash with Xiaoqing, which will then get us into a hands-on exercise where we highly encourage you to follow along and fill in the missing entries. And we'll do that in breakout rooms so that we can offer you help as well. All right, so I'm going to go ahead and stop there.